What you are seeing here is a Python simulation of an EKF algorithm being used for SLAM. As the robot is driving around, the EKF provides an estimate on where the robot is and where the landmarks are. In this video, I'm going to show you how you can code something like this yourself. Okay, so to start writing our code, I begin with an empty directory. I just call it EKF SLAM demo. And in this empty directory, I've cloned a Python package repository. Here is the link to that repository, and also I'll provide the link in the description below. But all this is a very lightweight, easy to get started UGV simulator for Python. Powered by Pygame, it should be pretty simple to install, everything to run, and I'll show you what this looks like to run. We're just going to go inside, oh, we already are inside, Python main.py, and I'm pressing the arrow keys to move forward and backwards, to pivot left and right. And that's pretty much it for this simulator. Like I said, it's supposed to be very lightweight, something where if you want to dig into it and look at the code, you can. We are going to use that as our starting point for this video. So I'm going to take that same script, I'm going to copy everything, and then I'm going to make a new file, and we're going to call this EKF main.py. This is going to be where all of our code is going to live for this video. Because I am taking code from one directory and putting it to another, I have to change some of the imports around. So this is going to be Python UGV sim.utils now. And the second thing that we need to change to get this to working is this map image path here. All I do is allow the loading of a generic background. I just call this map blank.png. It's included in the repo, but you can use any PNG that you want. This just has to be a path to it. And because we have a different path than that package, all we need to do is include that folder. So if I run this new file, let me back up, and if I run this new file, then let's see, Python UGV sim, if I can spell it correctly. Perfect. Same exact thing. As a quick intro, just to get us started using this simulator, I initialize Pygame. I define this NumPy array to be the initial initial pose of our robot. It's going to be the X position, robot Y position, and then the robot heading, which we'll call theta for this video. I take this NumPy array and I put it inside this constructor for this class called differential drive. That's the model of the robot that we're going to use. I define the time steps that I want to discretize everything. This is going to be the time step per iteration of our main logic while loop. I have aligned to initialize another object I just call environment. This is going to work with Pygame under the hood for the most part, so that we don't have to interface directly with it as much as we might need to. This is going to provide some helper functions for us. I include a Boolean running flag. I initialize to true. These are the controls for the robot. So the first element is the forward-backward velocity. And then the second element is the angular velocity. We want we enter into this main while loop. While running is true, I get all the events that Pygame has stored up, and if the event is to quit, then I set running to false, and then it exits that while loop at the next iteration. If the event type is either pressing a key, so key down, or letting go of a key, key up, then I pass this event to a function called robot.updateU. And this function does exactly as it says. It takes this U, takes whatever event. So if I'm pressing the up arrow or the down arrow or the right or left arrow, it just updates what this U is based on the model of the robot. With that U, we pass the control and the time step into a function called move step. This is just a really simple integration. So it takes the continuous time model for the robot, takes the controls, and it integrates forward by some really small time delta t. We use that environment variable that is defined here, and I call a function called showMap. What this does is redraw the background of the Pygame window. That's what we need to do for every time something happens. We need to redraw everything. So I redraw the background. I call a function called showRobot that draws a gray rectangle at the state of the robot. So it reflects the X position, Y position, and the heading of the robot. And then I call this Pygame function called updateDisplay. That's basically the simulator, and that's going to be our starting point for the EKF code. Now, I don't want this video to be a math-heavy video. I'm not going to go into the derivation of the EKF, but to talk about what I'm coding, I have to give at least some context to what it is I'm actually doing. So I'm going to base my implementation of the EKF on an algorithm given by this book called Probabilistic Robotics. The authors are Thrun, Burgard, and Fox. Sebastian Thrun is very well known in the space of robotics and autonomous vehicles, and this is considered a little bit of a Bible when it comes to mapping and other probabilistic processes in robotics. I am going to use the totally legal and free version of Thrun's Robotics, and they give in their SLAM chapter an overview of the EKF algorithm. So this is precisely what we're going to tackle in this video, and I am going to talk about the general steps. So what is our general game plan for this script? Well, the EKF SLAM logic, or extended Kalman filter logic, tracks two different variables. The first is the state estimate, which is usually denoted by Greek letter mu, and that is where our best guess of the state is. This mu includes not only the robot pose information, but also the landmark position. Along with this is the state uncertainty. Uncertainty, how uncertain we are of our best guess. The Kalman filter, right, the basis of the EKF SLAM algorithm, assumes that our uncertainty and our belief is modeled after a multivariate Gaussian. So in terms of this Gaussian, this mu is the mean of the Gaussian, right, where the Gaussian peaks, so the highest probability, and the sigma is the covariance matrix. These two variables are passed around two different functions, so two steps to the EKF. The first step is called the prediction update, and the second step is called the measurement update. The main thrust behind the prediction update, it tries to answer this question. From the control inputs, U and some model, how does our state estimate change? One thing that is important to note is that moving only affects the state estimate of the robot, right? We are not modeling any motion of the landmarks, so this prediction update should only change the mu's and the sigmas related to the robot. And one last little note I'll have here is that moving affects uncertainty of the system. So anytime that we move, we affect the system uncertainty. And then, of course, model noise also affects uncertainty. So these two are the main drivers of how this sigma changes. The measurement update is the part of the algorithm that tries to answer from what the robot observes, how do we change our state estimation. So anytime it observes landmarks in the environment, how do we update our state estimate? And the second note I'll have here is that we reconcile current uncertainty with uncertainty of measurements. So we take how uncertain we are of the total state, we take how certain we are of the measurements, and we have to reconcile these two. So these mix in a very special way in the EKF algorithm. These two steps are the main steps that I'll be coding up, and along with, defining all the variables and the matrices that go along with it, and then also plotting functions. But that's the game plan for today's video. All right, well, without much further ado, let's actually start writing our EKF algorithm code. The first thing I'm going to do is write a little section, and I'm going to call this EKF stuff. In this section, I'm going to write our two very important steps. One is the prediction update, and I'm just going to return. So I'll fill these in as we go along. And the other one's going to be called the measurement update. So the two very big important steps for our EKF algorithm. Above here, I'm going to define some important variables to help us structure our code. The first is going to be robot parameters. I'm going to define end state to be the state dimension of the robot. So x, y, theta. We have 3 different entries for the robot. And I'm going to also define the number of landmarks. Or just say 1 for now. The next thing I'm going to define is the variables that we're going to use for the EKF estimation. First one is mu, right? And this mu is going to be a column vector that has 3 entries, one for each state dimension of the robot, and then twice the number of landmark entries. So this is just the x position and the y position of the landmark. The covariance matrix is going to be the same number of rows, so I'll just copy. And it's a square matrix, so it has to be the same number of columns as well. So here we have 3 plus 2, so this will be a 5 by 5 matrix, and then this will be a 5 by 1 column vector, or 5 by 1 matrix, however you want to view it. I'm going to put in a section called helpful matrices. And this, let's see, clip out the section I'm going to focus on right now, right there. Let me go back to the code. So this matrix right here is something that shows up both in the prediction update function and the measurement update function. So I'm just going to define it outside to avoid redefining things. We can see it is a identity 3 by 3 matrix on the leftmost side, and then a bunch of zeros. We have 3 rows and then 2 times the number of landmarks for the columns. So I'm going to do that with the np block function. Okay. And then I think that is all I'm going to use to get started. The first thing I'm going to focus on is these 2 steps, or these 2 lines right here. This step in particular is the prediction update for the state estimate. It does not affect the state uncertainty at all. All it does is take where we think the state is. It takes the control inputs, so forward, backward velocity, and angular velocity, and the discrete time. And then it just translates and rotates what our state estimate should be. So it's just assuming our current state estimate. We just send that into the actual discretized model. Where does that end up? And that is exactly how we update our state estimate. So to help make the code a little readable, I'm just going to unpack this state estimate, and I am going to take the first 3 entries of mu to be the x, y, and theta for the robot. And that's a very standard interpretation of what mu is, but technically you can put those state estimates anywhere you want as long as you're consistent. I need controls, right? So forward velocity and angular velocity. So that is something I'm going to pass. I also need the discretization time. And I'm naming it u just because it's going to be the same exact u as is down here. So with those, we have the prediction update. We take this f of x matrix, we take its transpose, and then we matrix multiply it by this 3 by 1 matrix. So what I'm going to do now is make a 3 by 1 matrix and fill in each of these elements according to what is written down here. And I'll even make a comment of it. Update state estimate mu with model. I'm going to call this the state model matrix, np zeros. The first element of the state model matrix just going to go back, is this line right here. And I have it also off screen so that I don't have to go back and forth. So we have V over omega times NP sine theta plus omega times dt. Now here's the first caveat that you're going to encounter when coding this stuff up. You may notice that this expression actually has, when we're dividing, right, by this angular velocity, if the robot itself is not turning, this angular velocity is 0. Now this whole expression actually converges to a finite value as this omega goes to 0. So this theoretic or analytic expression actually is okay in the limit that omega goes to 0. But when we try to translate this to computer code, oftentimes it gets very, very confused about what we're trying to do if we actually try to divide by 0. So what we're going to do is include the case where this is almost nearly 0. So we're going to do this by saying if omega is, let's say, greater than some small number, 0.01, it takes in this value. We're going to exploit Python's nice syntax. If this is not true, then we're going to take the expression of this as omega goes to 0, and it should look very familiar. It's going to be forward velocity times dt times np cosine theta. So I think geometrically this should make sense, right? We take the component, how we're facing in the x direction, and then we just multiply by the speed times time to get that small step in the distance from our current position. Second entry looks very similar. This one has cosines in it. V over omega np cosine theta. And then this is going to be minus V over omega times np cosine theta plus omega times dt. Great. And then I'm going to do the same thing here. Only use that expression when omega is greater than some small value. Otherwise, we're going to substitute in the if I can type today. All right. So I think this should also make this same geometric sense as this line. The third one is the simplest. It's just omega times dt. Okay, so now we have the model matrix filled up, and we are going to say mu plus equals np transpose f of x dot this state model matrix that we just wrote. Okay, so that is the entire prediction step when updating the state estimate. Like I said, I'm not going to touch the uncertainty for right now. We just want to make sure that this code is working. Okay, so we have that step going on, but we also want to plot, right, this state estimate. Because what good is the code if you haven't actually seen that it works? Plotting stuff. Let's, there we go. Perfect. So we need some functions to plot. And again, not going into too much of the math, but one very standard way of plotting a multivariate Gaussian, at least a 2D multivariate Gaussian, is with a ellipse, or an ellipse for normal people, if I can talk correctly today. So what we're going to do is take the state x and y, those uncertainties, and then plot both of those onto our Pygame window. I'm going to write two functions. One I'm going to define to be, we're going to call it show uncertainty ellipse. This is going to take in the environment variable that I defined down here. Like I said before, it has functions under the hood that help us interact with the Pygame window so we don't have to do too much math for this visualization. The rest of the arguments is the center of the ellipse, the major and minor axis width, right? So every ellipse has two different widths associated with it. And then in general, these uncertainty ellipses are going to be rotated. So I'm going to include the angle of rotation as well. I'm going to cheat a little bit, and for the sake of time, just copy and paste in code that I have before. But I adapted this from a Stack Overflow answer about how to draw a rotated ellipse, and I made it kind of comport with what we want to do today. The logic is pretty simple. I have a target rectangle that I create from the center and the widths. I create a surface to draw the rectangle on. I draw the ellipse on the surface, and then I rotate that surface by some angle. And at the very end, I draw that ellipse to the Pygame surface. And that is a function of this environment variable, getting that Pygame surface. And then I don't think I need a return here. Okay, so this function is a very general, you give me centers and widths and angles, and this function draws the ellipse for you. So what we need to do is actually get what that ellipse is. And that function I am going to call show robot estimate. This is going to take in mu, sigma, and the environment variable. Going to unpack mu again to help us retain readability of the code. Alright, so the first thing to note is that this show uncertainty ellipse function actually takes in pixel units, and the state estimate and the state uncertainty are in units of meters. They are not the pixel coordinates on the Pygame screen. So the first thing we're going to do is translate what this x and y position are in terms of the pixel coordinates. And I am going to do that with a function inside this environment variable called position to pixel. And if you go to the function itself, all it does is take the size of the map and the number of pixels that define the map in the x and y direction, and then just figure out if the robot is in this x position, what should be its x pixel coordinate, and the same thing for the y. And it returns a tuple of x and y pixel coordinates. So that is the center. We also need our width and our angle. This width is likewise defined in pixel units. And we are going to, for right now, just define it to be, let's say, 50 pixels by 50 pixels. And then we're going to define the angle to be 0. And then we are going to call this function, show uncertainty ellipse, for the environment, center, width, and then angle. Okay, now that we have these functions for plotting, let's actually move on to implementing everything inside our main logic loop. We initialize the robot and time step here, and we actually likewise need to initialize state estimate down here. So our mu 0 to 3 is going to equal the initial position of the robot, right? We just initialize wherever we think the robot is at the very beginning of our simulator. And I'm going to use a function called expand_dims. And all this does is take this 1D numpy array, make it a 2D numpy array. Because our mu, right, is defined as a 2D column vector. And I think that's all we need to do for the state estimate. We need to write down the actual EKF steps within the main logic loop. So EKF SLAM logic mu sigma equals prediction update mu sigma, takes in the controls, and then it takes in this TT. This section I'm just going to call show ground truth, right? So I show what the map actually, the background of the map, and I show the actual position of the robot. And then let's say show EKF estimates. So this is where our show robot estimate is going to live. Takes in mu, takes in sigma, and it takes in environment. So if I did this correctly, EKF main, it should just work. Cannot unpack non-iterable none type object. Let's see. Prediction, so it's yelling at me for the prediction update, mu sigma udt. Mu, here we go. In my prediction update, I actually have to return mu and sigma. And I'm just going to go ahead and do that here in the measurement update too, so I don't scratch my head later. So before it was putting mu and sigma in and then returning nothing because I asked it not to return anything. Ooh, look at that. So just as a recap of what exactly is happening is the package, the Python UGV sim package, is moving this gray rectangle, right? That's our ground truth for a robot. But what we just coded up, this prediction update right here, so all this code here, that is what actually is moving where this red circle is. And you see that those two line up very nicely together. So that is a very good sign. Perfect. All right, so it looks like we successfully implemented this prediction update just for the state estimate. All right, so next we are going to incorporate the uncertainty inside our prediction update. So let's say update state uncertainty with model plus noise. And the section of the, go back to the algorithm, the lines that correspond to this uncertainty update are these two lines right here. And I'll bring that up. Get rid of one of those. Bring up the code again. Perfect. So what we're going to do now is code up these two lines. You'll see that we need to construct this matrix right here, which is a matrix that is essentially the Jacobian of our state model. It's the first derivative of the x and the y with respect to this robot heading. And we construct this auxiliary matrix G, and then we use this G to update the sigma from the previous sigma, as well as the noise from the random Gaussian variable that's added to our known state at every time step. So let's first write this matrix here, and I'm just going to call this state Jacobian matrix, and this is going to be a matrix of zeros that are going to be 3 by 3. Let me just make sure. Right. So I'm initializing this state Jacobian. The only non-zero values of this Jacobian are the first row third column and the second row third column. And the non-zero values correspond to how the x position changes for tiny changes in the heading of the robot. You'll notice that the model itself is independent of the x position and y position, and I think this makes sense, right? How the robot moves doesn't depend on where the robot is, but it does depend on where the robot is heading. So when we construct this state Jacobian, the non-zero entry is the first row and the third column, and just to save us a little bit of time, I'm going to copy over from my notes and paste this in. One small note I will say, if you look at this copy online, is that this is actually off by a sign, and this element is also off by a sign. So this should be negative, this should be positive, this should be negative, this should be positive. Turns out that this actually works out because we have this G defined like so here, and we have G times sigma times G transpose. This is like saying if it's either x or negative x squared, when we multiply it together, the sign just kind of goes away and it becomes positive anyway. So luckily this actually works out, but technically this should be negative, this should be positive, this should be negative, this should be positive, and so we're just going to do it correctly for our code. That should be right, dt. And then the last non-zero entry in this matrix is the second row, third column. And I am just going to, again, copy and paste over from my notes. All right. So now we have this matrix right here. And we want to construct this G matrix. So that G matrix, NP identity, we need the shape. One very quick way to get the shape of this G is just by looking at what it actually multiplies. So this G, the columns of G, have to match the rows of this sigma. And that's just rules of matrix multiplication. And the rows of this G have to match the rows of the sigma. So that means that the size of this G just matches the size of this sigma. So I'm going to take the shape of sigma, put it into the identity matrix function for NumPy. I'm going to add, let's see, NP transpose f of x dot this state Jacobian dot f of x. Perfect. Now I'm going to do this second line. And in order to do the second line, I need to define what this R is. This is the noise associated with This is the covariance of the random noise that is added to my state model every time step. So I'm going to come up here and define a section called noise parameters, and they called it R, so we'll call it R, and we're going to have a diagonal matrix, and the entries along this diagonal are the noise for the state of the robot as it every prediction step. This is the noise that's added to the robot state uncertainty. The first entry is the X position noise. The second entry is the Y position noise, and the last entry is the noise in the heading. The units of this X and Y are meters per time step, and then this is radian per time step. And you don't want to make this too big. Let's say if this were 1, then what I'm saying is that every prediction step, the robot's uncertainty in the X position actually grows by 1 meter. And because this prediction update is called every dt, and our dt is, if we go down here, 0.01, if this were 1, then every 1 second the uncertainty would grow by 100 meters. And that is a pretty poor odometry model if every second your uncertainty has to grow by 100 meters. So we're going to keep it quite small. And let's see, the next step, right, so we're still on the second step, and I'm going to just write it out. So sigma equals G dot sigma, the old sigma, dot NP transpose G. So this is how the state uncertainty transforms from the model, from the previous uncertainty. And then we're going to add to that, I think it's, yep, it's transpose Fx dot this state Jacobian matrix. Oops. Oop, lost my place. Where? Here we go. Dot f of x. So let's just double check. We got this identity matrix. We got fx transpose times the state Jacobian dot f of x. Great. And oh, what am I doing? I just caught myself. This is not the state Jacobian matrix. This should be R. That's the whole reason why I coded R up there. Okay. Now, this should be, right, G sigma G transpose f of x transpose R f of x nu sigma. Okay. So that in a nutshell, assuming I did everything correctly, is our entire prediction update. What is left to do now is to help us visualize the uncertainty. Right now we assumed a a hard-coded width and angle for this ellipse that we're showing. But now we want the dimensions of the ellipse to reflect the uncertainty in the robot position. To do so, I'm going to include another helper function. And this one, let me just check my notes real quick. I'm going to call sigma to transform. I'm going to put in a submatrix of this sigma. So I don't want the full sigma. I just want this submatrix. It's going to be a 2 by 2 matrix, and it's going to encode the uncertainty in the x and y position. And the reason why I'm making it its own function is because we can reuse this function not only for the robot uncertainty, what we're doing now, but also for the landmark uncertainty when we get to it. Okay, so in order to get the dimensions of the ellipse, we need to know what the ellipse means in terms of the uncertainty. And the typical, I guess, interpretation of the uncertainty matrix versus the ellipse is that the ellipse shows the eigenvalues and rotations associated with the sigma. The eigenvalues correspond to the major and minor widths of the ellipse, and then how the eigenvectors are rotated, right? This eigenbasis for this submatrix, how that's rotated is how the ellipse is rotated as well. And I think once we start plotting things, that'll make sense. Again, I don't want to be too heavy in terms of math in this video. We just want to get things going. Plus, this is also more geometry than it is EKF specifics. So NumPy has a function called eig, where if I put in this sigma sub, make sure I get the right variable, put in this submatrix for sigma, I can get out the eigenvalues and the eigenvectors. The eigenvalues are going to be the widths, so we're just going to return that, eigenvalues. But we also want to return the angle of rotation. And this angle is going to be taken, we're going to get it from the eigenvectors. What I'm going to do to find this angle is simply take the angle of the first eigenvector with respect to the x-axis in our global coordinate system. So this is in terms of our world coordinate system anyway, right? We have these eigenvectors in terms of that world coordinate basis. And to get what the angle looks like for that first eigenvector, I'm going to use the arctan function, specifically arctan2. Arctan2, the first argument is always the y value. And the y value for the first eigenvector is actually the first row, or I guess the second row, first column. These eigenvectors are ordered by row. So every row in this eigenvex variable is an eigenvector. The second argument is the x-coordinate. And one last thing we're going to do to this angle, right now it's in radians, and we want it in terms of degrees. For whatever reason, this Pygame transform rotate, its units for angles are degrees. So we are going to 180, 1/2 turn in terms of degrees, and divide by 1/2 turn in terms of radians. Okay, so now we have this generic sigma to transform function. What we're going to do is use this guy in our show robot estimate function. So first, let's use it to get the eigenvalues and the angle, sigma to transform. And again, we need this sub matrix of sigma that corresponds to the robot uncertainty. And that is just the first two elements, so the very top left corner or the top left block of this sigma. With it, we already get this angle, so let me just delete that. Now, this eigenvalues, again, units-wise, is in terms of meters. So we want the width of the, sorry, just exiting out some notifications. We want the width of the ellipse in terms of pixels so that we can draw it on the screen. This is going to be found using another helper function from this environment variable. And this one is called, let me make sure that I have it correct. This one is going to be called dist to pixel length. Let me see if I can turn off. Okay, sorry about that. Eigenvals 0. Right, we're going to input the first eigenvalue, use this function to get the distance, transform the distance in terms of meters into distance in terms of pixels. And then the environment, same thing. In fact, I'll just copy and paste. Okay, now we have this width, and we now input that into our show uncertainty ellipse, and the function that I had before already takes care of the sizing and the rotating. The last thing I'm going to do is talk about the initialization of this sigma, right? So far, the sigma is just a bunch of zeros, and it's good in general to initialize to values that make sense. So we are going to use a function called fill diagonal sigma, and let me scroll up with my notes just to make sure this all looks good. Yep. I'm going to fill the diagonal of sigma with a large finite value. The idea behind this is that all of the on-diagonal elements of sigma correspond to the actual variance of these things that we're estimating, right? The uncertainty of x, the uncertainty of y, the uncertainty of theta, and then likewise for the position of the landmarks. And we are going to initialize that to a big number. We have no idea where it is to begin with. And the off-diagonal elements are these correlations. So we're going to keep those as 0 because we don't want to assume any correlation between variables. That's actually, these off-diagonal elements are going to be populated by the EKF as we run through both the prediction state, the prediction step, and the measurement update step. So we initialize big numbers up there. Down here, when we initialize our state estimate, let us also initialize the state uncertainty for our robot. And let me get the good values. So I'm going to assume 0.5 in all directions. So for the x direction, y direction, and the heading as well. And that, I believe, is everything that is needed for this to start working. So let's try it. So without me moving, we can see that the uncertainty is growing every time step. And again, that growing is caused by this term right here. This is the noise that's added every time step, regardless of our motion model. As I start moving, we can see some funny sandwiching, and let me start over so we can see that better. If I start moving, you can see the ellipse kind of sandwiching in the direction orthogonal to the direction of motion. And the reason behind this is because when we start initially, and let me remove, so 0, 0, 0. Let me remove any noise that's added. So all the noise happens because of noise at the very beginning of our sim. And let me make that a little bigger. So let's say 0.1. So our starting uncertainty isn't growing anymore because I set that R matrix to all zeros. And if I move, you can still see the sandwiching effect. What's happening is the robot, when it starts out, has some uncertainty in the heading, very small uncertainty. So the robot is estimated to point directly upwards, but it could also be pointing a little bit to the left or a little bit to the right. And when that happens, we move forward. The robot, if the robot was pointing a little to the left, then our uncertainty in the x has to spread out a little this way. And it's the same if a robot was pointed a little to the right, then the uncertainty in our position should also spread out that way, right? Small uncertainty and angles start adding up as we move further and further along. So all this sandwiching is caused by the correlation between the uncertainty in the heading of the robot and the, in that case, X position, but whatever the orthogonal direction of the robot is. And let me bring these back so that we have noise again. All right, so it looks like we have a pretty successful implementation of the prediction update for our robot. Okay, so now that we have the prediction update completed and we are totally visualizing that and visualizing the state estimation and uncertainty for the robot, let's move on to the second half of the EKF algorithm, which is the measurement update. Now, step 0 for implementing that is just putting in landmarks right into our simulation. And to do so, we are going to first visualize the landmarks, simulate measurements between the robot and the landmark, and then visualize these measurements. To start, I am going to, at the very beginning of our code, define in a Python list, and let's just call this landmark parameters. And this is going to be a list of landmark positions, X position and Y position. And right now I just have a list of 8 different landmarks in our map. With this, we can immediately take out this kind of hard-coded value. Bye-bye. And place or set the variable in landmarks equal to the length of this list. Okay, now that we have these landmarks, let's visualize these landmarks. So I'm going to go to the plot and stuff section, make a new line, and just to keep this video short, I'm going to copy and paste a function that I have off to the side. This takes in landmarks, so the list of landmarks that I just defined, takes in that environment variable as before, and for each of the landmarks, I convert the position in units of meters, right, to the pixel units needed to draw this on the Pygame window. I do the same thing for the radius of this circle, or our landmarks are going to be represented by circles. You can choose any shape you want, so feel free to change this. And the radius of the circle I set to be 0.2 meters. So I just find how many pixels that corresponds to. And then lastly, I use this function called filled circle that just draws a circle at the pixel position with the pixel radius with some color. So I have this function, and let's include that down here. Show landmark location takes in the landmarks that I defined at the very beginning, and then takes in this environment variable. So if I do Python EKF main.py, we now have, in addition to the robot and its uncertainty and estimation, we also have the landmarks that show up. And I just have like this rectangular kind of shape for the landmarks, but feel free to populate these with maybe random placements and maybe play around with the number of landmarks as well. Cool. So that's visualizing landmarks. What we want to do with the landmarks is actually take measurements of these landmarks. So that isn't necessarily a plotting function. I'm going to put this in my EKF function, and let's just keep it here. So down here are my EKF steps. EKF steps. And I'm just going to call this measurement simulation function. We want to simulate measurements. This is also just going to be a quick copy and paste from my notes just to keep the time down, but let's see. Sim measurements is what I call it. Sim measurements. It takes in, what does it all take in? The landmark, the robot pose, X, and then the landmarks as well. So this is what the function looks like. It takes the robot pose and just kind of deconstructs it into X, Y, and theta for the robot. It creates a list of measurements that are just an empty list that's going to hold all of our measurements. For each of the landmarks in this list of landmarks, I record and keep track of not only what landmark it is, but also its index. And this L index is the, you might have heard of the correspondence of landmarks in the environment. And all that really means is when the robot gets a measurement, I know exactly which landmark that measurement is from. There's no ambiguity of, well, I'm getting this measurement, but it could be landmark A or it could be landmark B. There's no extra step to figure that out. I just know what landmark that's from. And we are just going to assume known correspondences. It's not too hard to incorporate unknown correspondences, but for simplicity, we'll assume known correspondences. For each landmark, we get its X and Y position. We get the distance between the robot and the landmark. We also get the relative heading. This is something that just adds a little realism. But as the robot's moving, right, the angle that the robot observes the landmark at is always relative to the robot frame. So to simulate what that would be, we get the angle of the angle from robot to landmark in the global frame, and then we subtract off the robot heading. So if let's say the robot in the global frame, the landmark is 45 degrees off away from the robot, but the robot is also facing 45 degrees, then it's going to measure a landmark directly in front of it. So that's what this line is all about here. This line takes this relative angle phi and just constricts it. It bounds it between negative pi and positive pi. And that's just going to be useful so that when we start comparing measurements, we know that, say, 3 pi is the same as pi. We don't have to do this later. We just constrict it right here. Now, this line just says if the distance of the landmark from the robot is less than the field of view of the robot, then it's a valid measurement, and I append it to this list of measurements that I'm keeping track of. And every measurement consists of the distance, this relative angle, and this landmark index. Note that we have some yellow squiggles. That's because we haven't actually defined this variable yet. So I'm going to do this under robot parameters, and I called it robot FOV, and we're just going to set that to 3 meters as well. So now we have a function to simulate measurements. The next step into just making sure this works correctly is visualizing this. And I'm going to go back down to the plot and stuff section, and I'm going to go make a new function. This function is going to be called, let me just make sure it's the same name as I call it in my notes. And in my notes I call it show measurements. I put in the robot state, I put in the measurements, and then I put in the environment variable that helps us, again, plot this to the Pygame window. Again, I'm going to copy and paste this guy just for expediency. I take the state of the robot and I again explicitly label x, y, and theta variables. In order to plot it to the Pygame window, I again need to convert from the units that are meters here into the pixel units that are needed for the Pygame window. For every measurement inside this measurement list, I deconstruct it into its three values: dist, phi, and index. You can see I don't really use the index here. I get the x position and y position of where the landmark should be according to this measurement. So I take the x position of the robot and I add this kind of offset, the range distance times the cosine of the angle. And because I'm plotting in the global frame, I have to translate to the global frame. So this is just the opposite of what I did before. Instead of subtracting off the robot heading, I now add the robot heading to get back into the global frame. Right, so I do the same thing for the y value. And then again, I take these x and y coordinates and I translate them from units of meters to the pixel units. And then I just draw it. I draw it as a line from the robot to the landmarks. And we need to take this function, show measurements, and put this into the logic while loop. And let's do it after we show the location. So let's say show measurements, and this takes in the robot pose. I'm not using the estimated pose, I'm using the ground truth, right? Because it's the ground truth where the robot actually is that determines the measurements that we have. So I'm going to get robot get pose, and then the z's are going to be, actually I take that back. I am taking that back. The measurements, when we plot them, I guess it depends on how you want to plot them. We can plot them with respect to the actual robot. Oh, yeah, okay, sorry. Going back on my going back, let's keep it the pose of the robot that we're plotting with respect to. What are my other arguments? The z's. So I haven't actually gotten those yet in my environment. So let's get those. Let's get the measurements after we move the robot. So get measurements. And it outputs a list of measurements. And the function is just called sim measurements. This takes in the robot get pose, right? Simulating measurements should be based on the actual pose of the robot. Takes in the landmarks as well. That's about it. So I get the measurements, and then down here I show the measurements. And I choose to show them with respect to the robot's ground truth pose, but you can, I guess, in more realistic scenarios, you can put in the estimated pose of the robot using this mu value. So let's just see what this looks like. So if I drive close enough, now we see these gray lines appearing between my landmarks. And these gray lines only appear when I'm close enough to the landmarks. And we define that field of view radius to be 3 meters. Cool. So now we have a successful visualization of the landmarks, a successful simulation of these measurements, and then a successful visualization of these measurements as well. Okay, after all of that, we are finally ready to start getting into the second step of the EKF, this measurement update. I would argue this is the hardest part of the EKF SLAM to actually implement, just because if you mess something up, it's really hard to tell what you messed up. And I know for me, it took me a couple days to go through all the math. I mean, at some point, stuff like you just have to rely on going line by line and making sure, is this correct? Is this correct? There aren't too many sanity checks that you can actually do to make sure this function is working correctly. So that's what makes it so tough. Don't feel bad if this is your first time and it doesn't work perfectly the first time that you try to implement this. Patience is key for this one. I know for me, it took me a couple days, so don't feel too bad. But we won't let that discourage us. We are just going to dive in. And to start, let's look at the portion of the algorithm that corresponds to our measurement update. So let me bring this up. Bring up the code. Okay. Maybe make this a little bigger. So what the measurement is all about, right, is taking these simulated measurements and using those to inform not only the state estimate, and this is going to change both the robot state estimate and the landmark position state estimate, but also the uncertainties around the robots and the landmarks. And this being a pretty large multivariate Gaussian, it's hard to exactly picture how everything is connected. The only chance that we three-dimensional beings have of seeing this is looking at the 2D output of the position estimate and uncertainty estimate for the robots and the landmarks separately. So just going through this whole portion of the algorithm, first they take the index of the landmark to be known, and that's again what we assume, right? We're assuming we know the index of the landmark, this correspondence. There's no ambiguity between if we receive a measurement where which landmark that actually came from. If we've never seen a landmark before, then we don't know initially where the estimated position of the landmark is. So all we can do is take it relative to the current estimated position of the robot. And then they go through and define some helper variables. They define the estimated measurement. They define some helper matrices, H and K, and then finally with all these things that they define for every observation, they update the state estimate and the state uncertainty. One thing I'll quickly mention before we actually start writing the code is that this S variable they call a signature of a landmark. This is something that we're just going to ignore. You can include it if you want, but for the most part, I'm just going to ignore it and just stick with the meat and potatoes of the range and bearing measurement. All right, so we are first going to include in our measurement update input the list of measurements that are taken from that simulated measurement function. And let me bring my notes on the other screen. Right. So we're going to start by setting the variables as we've done before, just to make our code more readable. You don't have to do this. We are going to keep track of these several different variables. You might see that the for loop actually ends here, and the actual lines of updating occur outside the for loop. So things that we calculate inside the for loop are used outside the for loop. So what I'm going to do is just create a list of several different variables to keep track of the matrices that are important in this step. And the three matrices that are important are this, I'm going to call delta Z. this K matrix and this H matrix. So the first one is going to be delta Z's. This delta Z, these delta Z's variable is just a list. Every delta Z comes with a NumPy 2x1 array of zeros. That's how I initialize it. And I iterate over, I make one for every landmark in the environment. And this is 2x1 because the measurements, every measurement comes with two values, a range measurement and a relative bearing measurement. The next thing I'm going to keep track of are those K matrices. So these guys, see these guys right here. And in order to get the shape of this K matrix, you can look at this line right here. Every K matrix, its row has to match up to the number of rows in this mu. And the number of rows in this mu is just the number of state elements that I'm estimating. So this is 3 for the robot plus 2 times the number of landmarks. And you can see over here, all I did was construct again a NumPy array of zeros and take the number of rows from that mu. The number of columns of this K you can get from the number of rows for this delta Z. And again, because every measurement is just a range and relative bearing, we just have a 2x1. This Z minus Z hat is going to be a 2x1 matrix. So each K is going to have 2 columns in it. The last thing that I'm going to keep track of are these H's. So this H value right here. And the shape of H is going to be the number of rows. So again, we're not considering the signature value of these landmarks. So we're going to pretend this last row and column aren't there. So that means that we have 2 rows for every H. So that is my 2 right there. And the number of columns, it's actually not 1, 2, 3, 4, 5, because we're actually multiplying by this matrix that we compute right above, f of xj. And this has the number of columns being just the number of states in mu. So 3 states for the robot, and then 2 times the number of landmarks for the x and y positions of the landmarks. So those are the things that we're going to keep track of. We are going to start with the for loop. So for every z in z's, I'm going to unpack it. So the distance, the phi, and then the index of that landmark. I'm going to splice out the mu that corresponds to the landmark location. And this splicing takes a little bit of sitting down and thinking about how all of the indices work, but the splicing occurs starting at the index, that is n state plus 2 times the landmark index. So if the landmark index is 0, then I start splicing at the third, right? Start splicing at a value of 3, because the first 3, 0, 1, 2, are for the robot. 3 is where the landmark positions start. And then I'm going to splice 2 elements over so that I get the x position of the landmark and the y position of the landmark. And then this splicing is always offset by the index of the landmark that I'm looking at. I'm going to include an if statement, the same one as before, and we want to track any time that we haven't seen this landmark before. The way I elect to do that is by initializing, I'm going to do this up here, I'm going to initialize my state estimate to be all nans, or not in numbers, nans in Python. So anytime I haven't interacted with a certain element of mu before, it's just going to remain not a number. You might say, well, if you do this, then this also affects the first three elements, right? The robot elements of mu. And that's true, but I actually overwrite them inside this main loop with the initial state of the robot. So after this, the only elements of mu that remain not a number are the ones that correspond to the landmark positions. So my if statement is going to look like this. If mu landmark, let's take the 0th or the x position of the landmark, if that is not a number, so we haven't seen it before, then what we want to do is populate our estimate of the landmark position with the estimate of the x estimate of the robot displaced by the measurement that we received. So the distance of that measurement and the relative bearing of that measurement. So this is the initial estimated x value of the landmark. We're going to do the same thing with the y value. And then just to complete everything, I'm going to take the same exact elements over here and then update them so that this mu now is no longer not a number. This mu is populated with this initial estimate of the landmark location. Okay, so that is this if statement here. Next, we're going to write up these helper variables. One is called delta, and that is just the x displacement and the y displacement between the robot and the landmark. So this is the landmark x, the landmark y. What is that x and y displacement? So I'm just going to copy and paste over from my notes. So I call it delta mu landmark minus a numpy array that contains the x and y estimated position of the robot. We have another helper variable called q, and that is just the norm of this displacement, right? The norm of this vector between robot and landmark. And I am going to use this numpy linalg norm function, pass in this delta, and then it's important to remember to square it because this actually gets us, right, this Euclidean 2 norm, not the actual squared distance. And this is actually the squared distance. Cool. So with these, we are going to construct the estimated measurement, right? If we say we get a measurement from the landmark, what this is saying is, well, if we actually saw a measurement from the landmark, what were we expecting to see? And we're going to compare this expectation with the actual measurement. And that actually happens down here, this delta z. So this comprises of the distance, comprises of the relative heading, and then again we're ignoring this signature variable. So I am going to compute the estimated distance, estimated relative bearing, again using this arctan and using the fact that this delta has already contained this delta y and delta x, and then we subtract off the estimated robot heading, And then what I'm going to do, I'm going to be fancy. I don't know if it's actually fancy. I think it's fancy. I'm going to take this phi estimate and pass it through, again, this arctan2 function, passing that phi through the sine and through a cosine. And all this does, again, like I showed before, it just constricts the phi estimated value to be within negative pi and positive pi. So we don't have to worry about this discontinuity between multiples of pi, or multiples of 2 pi. Okay, with that, I'm going to construct the estimated, an array that contains the estimated measurement values, so this estimated distance and estimated relative bearing. I'm going to construct an array to contain what we actually measured. And then here is where I'm going to start storing this difference. So it's the actual measurement minus the estimated measurement. So here I use the index of the landmark that I'm looking at, and I just I find the element in this list, and I just replace it with this difference here, and we're going to call that outside this for loop when we're done iterating over all of the measurements that we do. Okay, the next part goes into constructing this H matrix and this K matrix. So they call it fxj. The shape of this is just the block matrix again. I'm reusing, if you remember, this f of x that I defined up here, because this f of x is just what's on top here. So I'm putting that on top of my f of xj, and what's on bottom is mostly zeros, and what we're going to do now is define the non-zero elements of it. And just to save time and keep this video short, I again am just going to copy and paste. So on the bottom, we are, get rid of this guy. On the bottom, we are splicing from the element that's right here. And again, you just have to sit down and reason about what that element is going to be. Oh, I see what's going on. I see what's going on. So I shouldn't take that out. We need to worry about the rows as well. So the rows are 1, 2, 3. So we want 4 onward. And we know there's going to be only 2 rows because, again, I'm cutting off. I'm not worrying about the signature of it. So we are going from row 4 to 5. So this is what this splicing signifies. And then to actually get the correct columns, I have to do exactly what I did before when splicing off this mu landmark. It's exactly the same. I get the state. I offset by the index of the landmark that I'm looking at. And then I splice from that variable over 2 entries. And then I say that is going to be an identity matrix. And again, only 2 by 2 because I'm not looking at the signature. So I'm effectively eliminating an entire row out of this and an entire column out of this guy too. Okay. So now that we have this matrix, we want to construct this matrix that they call H. And just as another warning, the book actually has incorrect signs for these elements. I don't know if they corrected it. They probably corrected it in like the actual printed or the official versions, but at least for this free PDF, these are wrong. So just beware as you're coding this on your own. I'm going to copy and paste the actual answer for this H, and this the signs that are wrong are the sign on this guy. This should be negative. The sign on this guy should be positive. The sign on this guy should be negative. And then the sign on this guy should be positive. And if you're doing this yourself, and if something's going wrong, I would definitely check this matrix because I found a couple errors when I first did it. Also note that even though there are like square root of q's in here, you're also dividing everything by this q, right, by this square distance. So I just elected to include these q's. So square root of q divided by q is just 1 over square root q. And then, yeah, I just include the 1 over q inside all these elements rather than try to keep track of everything like by taking out this q. Okay, so this is this portion of the matrix. We need to right multiply by f of xj. So h equals h dot f of xj. And then we are going to add this h to the lists of h's, again using this landmark index. And then we are going to construct the K matrix. So if I look at it again, we just take the old sigma, we multiply by H transpose, and then we multiply by the inverse of this guy inside the parentheses, H times old sigma times H transpose plus this Q. And I don't believe we've actually written this Q yet. Yep, so you can see that the PyLinter is actually highlighting this and saying that this Q isn't defined. Thank you. We are going to go back up to our noise parameters and then just include Q up here. So that's going to be our Q. And this, again, has units of, so this would be meters, right? This is a distance. So distance per, I guess this would just be a distance because this isn't actually happening. This isn't a part of the model. This is just be units of distance. And this is just saying for a given range measurement, how much off do we expect the actual range measurement to be? What is that variance? And then the same thing for the relative bearing measurement as well. Okay, so now we see that the Q is defined. Cool. And then, yeah, we store it here. And we'll go back and just take a note, not the page. We want the clipped version. We'll just note that this completes everything inside this for loop. Cool. And again, I'm just copying and pasting. When you actually write it for yourself, take your time and debug as needed as things crop up. Okay, so now we are outside this for loop. I am going to store everything in variable called mu offset, and a variable called sigma factor. This mu offset is just what I'm going to add to the old mu to get the mu new mu. Oh, look at that, I'm drawing stuff. I didn't even realize. Let's erase. Ah. Cool. All right. Yeah, so this mu offset is going to be this quantity here, and this sigma factor is going to be what we multiply the old sigma to get the new sigma. I'm going to initialize this, and the shape of mu offset is the same shape of mu. Oop. There we go. And the sigma factor is going to be numpy identity sigma dot shape 0. Cool. Now what I'm going to do is create another for loop, but instead of iterating over every measurement that I make, I'm going to iterate over every landmark index. So landmark index in range and landmarks. I'm going to update what this offset factor is. You can see this summation. So this for loop that I'm writing is essentially just this summation. Start out with zeros for mu offset, and I add on this K matrix corresponding to the same landmark, and I multiply by the difference, this difference vector, this delta Z. Sigma factor starts with an identity, starts with this I, and then progressively subtracts off more and more for every landmark that I have observed. And just as a note, for any landmark that I haven't observed, I initialized all these K's and H's to be 0. So if I haven't seen any landmarks, this should be 0 times 0, so this should not change, and this should be 0 times whatever this H shakes out to be, so this should just be the identity. Okay, so now that we have those two, I'm just going to say mu plus equals mu offset, and then sigma is just sigma factor dot the old sigma. And it's yelling at me. Okay. It's just a little slow. Cool. So, again, the process of just writing this and then just seeing what is output, you just have to bite the bullet and do it. Unfortunately, there are no sanity check small steps that you can do, at least that I'm aware of. So now we have an updated mu and updated sigma. This updated mu and updated sigma contains all the information about our robot state and our landmark state. And the very last thing that we need to do is to visualize, right? Not only the robot uncertainty, right? An ellipse for the robot, but also an ellipse around every landmark as well. So I'm just going to put it right under show robot estimate. We're going to define and call it show landmark estimate. And let me just go to my notes. I'm going to include all of mu, all of sigma, and then once again use this environment variable to help us plot and convert units. And I am going to copy and paste what this visualization is. Again, this isn't inherently about the EKF. This is just about visualizing our results. For every index, for every landmark index, I again splice our estimate according to, or I get the state estimate of the landmark, right? So this is the x position of the landmark is mu at this index location here. I get the y position of the landmark at this location here. And then I also splice out the sub-sigma matrix, right? That sub-matrix in the giant sigma matrix, the total sigma matrix. And I do the same splicing as before, the same kind of index logic by offsetting by the number of states, as well as the index, the landmark index that I am looking at. And then this is, again, a 2x2 matrix. If the landmark has been observed, this is going to be a number, right? So this is going to be true if it has been observed. I do the same stuff as before. I get this pixel location of the landmark. I translate from units of meters to units of pixels. I get the eigenvalues and the angle from this sigma to transform function, the same exact one that we use for the robot. I include an if statement. I found that if the eigenvalues are super big and it tries to draw these ellipses that have giant major or minor axes, for some reason it slows down Pygame a lot. So I just include this and say if something is over a 15 meter uncertainty, then just don't bother drawing it. It's just uncertain at that point. But if it's under, then I get the, let's see. Yep, I get the two eigenvalues. I find the distance in units of pixels because these eigenvalues are in units of meters. And what I do is take the maximum between that and 5 so that even if the eigenvalues are super small, I at least see a little bit. If the ellipses kind of collapse down and it has a width of 0, it's not going to show anything. So in this way, it at least shows a little bit. I do the same thing for the second eigenvalue. And then I use the same function that we used for the robot, showing its uncertainty. So with all of that, right, the measurement update and visualizing the landmark estimate and uncertainty, we, I think, are ready to include it inside our main logic function. So let's include it right after we show the robot estimate. Let's also show the landmark estimate. And I just include everything as before. Okay. I guess instead of Control S, I just typed Control Z. There. Okay. Now, if everything is right, we should be seeing ovals and ellipses. Let me pause this recording real quick and see if I can figure out why we aren't seeing anything. Okay, so after some quick debugging, I actually found that I never actually called the measurement update. So this whole function that we wrote, I never actually called inside the main logic loop. So now that we have that in there, we have the EKF SLAM logic performing a prediction update and then a measurement update. we can finally start plotting things. The first thing I want to show is what everything looks like when there is zero noise in the heading of the robot. So if I go up here, I have no noise in the robot's heading for my R matrix. I have no noise in the bearing measurement. And then I also start out with no uncertainty in my robot heading. So everything about the heading and angles are known. And I'll start plotting. And you can see, just as before, this uncertainty starts growing. Let me replay. I'll go over here and I'll observe this landmark. Once I observe the landmark, you can see that the uncertainty of the landmark kind of inherits the same uncertainty of the robot that I observed it from. And once I start observing, then the uncertainty of the robot stops growing, right? Even though I have model noise that is expanding the circle, because of the measurement update, the EKF SLAM is reasonable to enough say, well, I keep seeing this certain measurement, and I have a very particular uncertainty with that measurement. So because I keep seeing this landmark some distance away, I no longer am this uncertainty doesn't grow. If I stop observing, this uncertainty starts growing. And if I go and view the same landmark, the uncertainty shrinks back down. So the fact that I see this landmark first and it has a very low uncertainty is very important. So if I continue driving on, let's say my uncertainty expands, and then I see a second landmark. Again, it inherits the uncertainty of the robot at the state that it sees this landmark. I go away. The uncertainty expands. I'm driving, and then I see a third landmark. If I go back, let's say to the second landmark, then not only does the uncertainty of the robot shrink down, but the uncertainty of this third landmark also shrinks down. And this is where the off-diagonal elements of that sigma are coming into play. The correlation between the x position of the robot, of this landmark, and of this landmark. And the EKF is intelligent enough to handle all that. So let's expand our uncertainty, observe a landmark, expand our uncertainty, expand, observe a landmark, expand our uncertainty, observe a landmark. Oh, too quick. I want this one to be really, really big. So let's wait a second or two. Okay, I'm impatient. So now we have this map, and I'm about to observe this first landmark again. In SLAM, there's this concept called closing the loop. And when I first learned about it, I always felt that it was some special step in the SLAM algorithm that actually happens when we see something again for the first time. But in reality, it's actually just a consequence of these two steps as we've coded them. Just like up here, when the uncertainty of this landmark kind of collapsed this uncertainty of this landmark, the same thing is going to happen. When I observe this landmark, it says, well, I'm very certain of where this is globally, and the robot is pretty uncertain of where it is. Because this uncertainty is so small, then the robot uncertainty is going to inherit now this lower uncertainty from the measurement update. And when I do, don't blink, it now affects the uncertainty of this landmark, this landmark, this landmark. All these other landmarks are updated. So this is just showing that this closure, this loop closure, isn't really a step in the SLAM process. Is actually just a consequence of the fact that anytime the very first thing that you see is by design going to be a very low uncertainty. So that anytime you see that again, everything that you saw before where your uncertainty might have been growing and growing, you snap your robot state, its uncertainty snaps back to that low uncertainty state. And because of the correlations between all of these variables that you build as you travel, the correlations when you do this measurement update say that, okay, well, because this is such a low uncertainty, this X position correlates with the robot X position, but that's also very correlated with this landmark X position. And that just kind of propagates backwards from this landmark that you observe. So very, very cool property of this SLAM algorithm. And as I drive around more, then these uncertainties start to reduce more and more. Yeah, look at that. Very cool. Another property of this whole algorithm is the fact that your uncertainty can only be as good as the first landmark that you observe. This first reference in the environment can never be any better than this. The circle is never going to be any smaller. I'll show one more demo, and this time I have some uncertainty in the robot heading as well as the bearing measurement. And you'll see now we have these correlations happening between the X and Y position. And this is where we get those ovals from. But the same logic of all this stuff still applies. So we still have loop closure. Now we just have these sandwiched kind of systems. So that's pretty much it for me today. I'm sure there are tons of other stuff that we can do to maybe optimize this code, but the whole point of today was getting things just working, right? And playing around and seeing it actually move and figure out the map as we drive around in Pygame. So I want to thank anyone who watched my video. I encourage anyone to learn more about the EKF if they're interested. And like I said, there are tons of videos and books that actually talk about the theoretical mathy derivation of all this stuff. I just wanted to today go over how one might actually write this in Python. And yeah, thank you very much. Let me know if you have any questions about this code.